Hi everyone, I'm Kaan Akşit, an associate professor from University College London in the United Kingdom. Thank you for joining this talk. Today I will be describing our HoloBeam project. HoloBeam offers a new milestone for building slim virtual reality headsets and augmented reality glasses with a wide field of view and high resolutions. So this work results from my collaboration with Yuta Ito, an associate professor from the University of Tokyo in Japan. So both virtual reality headsets and augmented reality glasses are improving quickly, and we have seen new products rolling out in this short time since the start of 2023. In addition, an alternative product emerged last year, offering a screen that shows three-dimensional images on a desktop display when placed close to a user's face. Virtual reality headsets, augmented reality glasses, and headsetless virtual reality products have common problems. The top 5 primary ones are form factor, heating, weight, power, and compute demands. You may be a student or an expert willing to learn more about these issues. We provide a detailed report at Eurographics back in 2019. This paper is highlighted at the bottom of this slide, and you may want to learn new skills for developing next-generation display technology. In that case, we encourage you to visit our course page from SIGGRAPH 2022 and to meet experts and other researchers or people relevant to displays, cameras, perception, and rendering. Join our Slack group. Finally, you can hear more from the display experts weekly by joining our seminars. So to address the highlighted issues explained in the previous slide, we proposed a new display technology back in 2021. At the time, we named it beaming displays. In our original proposal, instead of placing active components such as computing units, batteries, or light modulators directly on a wearable device or a device standing close to a user's eyes, we argued placing all active components on a projector and beaming images to a user from a distance. In this case, users wear lightweight passive components of diffractive or refractive optics, such as gratings or lenses. In our previous implementation with beaming displays, the wearable portion of our prototype was still bulky, as shown in the left photograph. The image resolution is limited to 7 cycles per degree with a wide field of view, with a field of view of 35 degrees. Although beaming displays offered an exciting opportunity and a new breadth in the design space, the promise of light form factor, high resolution, and wide field of view still needed to be achieved. HoloBeam asks, could beaming displays rely on holography to improve their optical capabilities? For this purpose, firstly, we had to invent a computer-generated holography pipeline that could offer more realistic images, which we did in our other paper at this conference. Please visit our presentation if you're curious about greater details. In addition to the holography pipeline, a new hardware layout is necessary to help project three-dimensional holographic images to a user from a distance, such as a meter away. We derived 2 new hardware layouts for this purpose, which I will talk about now. Our first layout is a cheap and slim version, but with amplitude-only modulation. This prototype shows how easy it could be to build glasses with sub-millimeter thickness. Our hardware starts from a cheap laser diode driven by Arduino. Light from that laser diode is modulated using an off-the-shelf amplitude-only digital micromirror device, also known as DMD. The diffracted light from that DMD is filtered and projected towards a user using a 4F system made of conventional lenses and a pinhole. As you can tell from the photograph, the user only has to wear a holographic optical element functioning as a magnifier glass with a thickness below millimeter. So note that the holographic optical elements, which are also known as HOEs, are transparent components and can only magnify the light projected in the proper direction. To record HOEs, we built our setup in our laboratory, and we verified the recordings with simple experiments. Our paper also provides a design space analysis for our HOEs. For more on HOEs and their capabilities, please consult our paper. The final product leads to the form factor shown in the photograph on the left-hand side. The images one can observe with this implementation are also captured in the photograph on the right-hand side. So although this is a slim and cheap implementation, image quality is decent, but the field of view is limited. We believe this is because of the projector, the way we designed it. Our next prototype, which we will describe today, aims to overcome this issue. So our next layout is an expansive version with phase modulation. Here you can see our hardware layout again with a fiber coupled laser and going into a phase only spatial light modulator. Note that phase only modulation helps to redirect light in an intended way rather than blocking light as in the amplitude modulation. The modulated beam is again filtered using a 4F system and a pinhole. The generated multiplane images at the end of the 4F system are magnified and projected towards a user using a projection lens. Finally, a user wearing a magnifier glass, in this case me, is shown on the right hand side, perceives three-dimensional images. So like any other holographic display, we need a 3D hologram generation pipeline, and we mentioned that we formulated one with our other paper at this conference. However, the HoloBeam takes an extra step. HoloBeam paper shows that we can quickly learn that pipeline with our new learned method. The exciting part of our learned pipeline is that the input RGBD images with depth information could be replaced with only RGB images without depth information. This is interesting because pictures are a more common way of storing visual information than depth captures. This new method offers a way to generate holograms from your good old pictures and photographs without depth information. So we should also mention that this estimation runs about 20 to 30 milliseconds per hologram, whereas optimization takes tens of seconds on a decent GPU. Let's look at this prototype's image quality and field of view too. Here you see a photograph taken from our eyepiece showing an image with 24 cycles per degree and 70 degrees monocular field of view. Compared with beaming displays, this is a considerable improvement in resolution and field of view. You can compare the numbers on the right hand side and see for yourself. Here I provide more sample images from our prototype. The prototype can also display color images as depicted on the right hand side, so there is no limitation on that. So looking at the overall image for HoloBeam and what it has achieved, HoloBeam improves on beaming displays most definitely, provides a powerful alternative to existing literature. However, there are open questions related to HoloBeam's next steps. To name a few, the eye box is limited in HoloBeam like in many other holographic displays. Resolutions could go even further and the users have to be fixed in front of the projector. It's making this HoloBeam not an ideal candidate to replace wearable near-eye displays at the time being. But for constrained scenarios like automotive or office use cases, it could be a strong candidate. In the following steps, we will focus on fixing these issues related to eye box, mobility, and more resolutions. So we also report potential ways in our paper. So there are lots of different display types which are all depicted in this figure, and green box shows HoloBeam or the beaming display. So with this work, we are asking ourselves, with improved resolutions and wide field of view and slim form factor, could HoloBeam help shape the next for the display technologies? So it's a bold step towards a brighter future. With that, I would like to conclude, and I'm more than happy to have any questions you have. Thank you for listening.